Hello students. We didn't get a chance to cover 1.4 experimental design, so I'm going to start on slide 43, which we had talked a little bit about, maybe like misleading graphs. So basically there, a misleading graph could be something to the effect of maybe number of doctors and number of patient deaths. And what would happen in most cases was that as doctors increase, patient deaths would actually increase. Now, there is a confounding variable here that if you can think about what happens in both cases, why is this, right? Doctors aren't killing patients, obviously. So the confounding variable that's here, kind of like a z variable, would be the increase in population or the population of patients. I'll just put patients. Right, the number of patients. So as patients increase, it turns out that number of doctors increases and number of patients. Sorry. Do you have a class here actually?
No.
So the confounding variable again is the number of patients because that increases number of doctors and number of patient deaths. So it's kind of like this z variable that influences both the other variables and makes it appear that there's something going on, but all we can say is that there is correlation between number of doctors and number of patient deaths. Okay, we cannot say that, or I'll just say this: correlation does not imply causation. Correlation does not imply causation. Okay, so this is one place where a graph could be somewhat misleading, might lead somebody to believe that the more doctors there are, the more patient deaths that would occur, which is not true. Okay, so moving on. We talked a little bit about observational studies, which observational studies would be where you're kind of like a fly on the wall, you're observing, but you don't impose any treatment or impose anything onto a subjects, okay? Which could be people, animals, computers, so forth. Now, there is a couple of different types of designs. They start you on the next slide, A. If you look at that picture, you'll see two treatment groups. One is women, and then the placebo group is men. So let's say you have this new weight loss program, and the 5 people that you treat with this new weight loss program are all women. And you're going to compare that to men who did not receive the weight loss program. No. Yeah. So this is not a good design, basically because you are comparing females in a weight loss program against males. That is a bad experimental design. You should probably mix males and females in both groups. Okay, so that's an example of a bad design. So let's move to B, which is a completely randomized design. This is one way you would like to do this appropriately. So you number subjects, and in the picture you'll see 10. And so that's a random sample of 10. From that 10, you're going to randomly select, you would number them 1 through 10 and randomly select 5 subjects into the treatment group, maybe like the exercise or the exercise program group, and you're gonna do the other 5 in the placebo group. So then you have something to compare, right? So if I compare them, have them do the workout program, 5 weeks later, look at the results. Yes, the treatment group had better results than the non-treatment group, or no, they didn't have better results than the non-treatment group. So the exercise, we can draw some conclusions from the exercise program from there. The third, or the second method on part C that you'll see in the picture here, on slide 44 is kind of like the stratified. You break them up into like groups, and then you randomly select a few from each group. Okay, except this is with an experiment, so you break them up, as I show there, into women and men, and they randomly selected maybe 2 women into the treatment group, and then 2 men into the placebo, into the treatment group as well, and then the rest would go into the placebo group. And then you would say, so maybe the ones selected, basically the ones colored in, the pink women and the blue men, you would well, you wouldn't see color, so but it's going to be on Blackboard. Okay, so you'll see the PowerPoint there. You'll see the pink women and the blue men. Those are the ones that's part of the treatment group, or the colored in women and men. And then the rest would go into the placebo group, or in other words, the non-exercise program in my example, okay, that I'm discussing. So in randomized block, you're going to form a block of women. So block is like the strata, okay, kind of similar to strata. And then you'll form a block of men, and then from each block you select a few. Okay, in this case they selected 2 each. Okay, so then D is another common type of experimental design, which would go very well with our example here of the exercise program. So it's a matched pairs design. Okay, so here you have Alex, Bob, and Chris. You're going to match present Alex, Bob, and Chris to future Alex, Bob, and Chris, right? So maybe one thing you might be interested in is getting weights or BMIs or strength in certain exercises. So these are all statistics that you can record pre, and then you could also do a post of those same statistics to measure, to see if there's any significant difference between those. So that would be a good matched pairs design. Okay, so here a little bit more on those, but it's basically what I was saying. But if you look at this, you'll see what a randomized block is, a matched pairs design, and also the completely randomized design. Okay. The last bullet there on slide 45, it says rigorously controlled design, carefully assign subjects to a different treatment group so that those given each treatment are similar in ways that are important to the experiment. This can be very difficult to implement, and often we can never be sure that we have accounted for all the relevant factors. So you do want to have controls, right? So if I'm measuring a new fertilizer on different plots of land, I don't want to give certain plots more water than other plots, right? And I want to try to make sure also that they have the same soil, so that I'm only testing what I want to test and nothing else. So I control, or as much as I can, I try to control all other factors. Or if you have plants inside, maybe a science lab, you got to be cognizant of whether your plants are going to be close to windows where there's more sunlight, or maybe in like a dark closet, right? Because plants probably won't grow, certain plants probably won't grow as well there. Other things just in general about experiments. So scientists will basically put out studies, and there's a couple of important standards for this, and maybe I get into this in a little bit, but no, so I'll just talk about it here. That you must be able to replicate somebody else's work in order for it, and that's what scientists do. So they post their research, and another scientist from somewhere else will say, okay, well, let me try that. And so they try the same study, and if they can't replicate the results, that doesn't look very good for the original scientist that created that, right? So science can be created by anybody, somebody that, my parents always have these remedies. They talk about ajo or garlic, and say, garlic's good for so much things. And so somebody could have had that idea, and like folk medicine and say, okay, well, let's see if this works, and you put it to a study, and then you can maybe do one of these designs and test it. So experiments is the only way that you can prove causation, not by observational studies. You cannot prove causation by observational studies, but the experiment has to be randomized, have to have an element of randomization using one of the designs we've discussed, and it also has to have some form of being able to be replicated. Okay. So other than that, I gave you some questions here. So it says identify which of these designs on the next slide, slide 46, which of these designs is most appropriate for the given experiment, completely randomized block, or matched pairs design. First one says, a drug is designed to treat insomnia. In a clinical trial, the drug amounts of sleep each night are measured before and after subjects have been treated with the drug. Okay, so this would be a case of matched pair because each subject, they measured the amounts of sleep each night before and then after. They matched them with their stats before and stats after. So that's a matched pair with the before and after. Currently, so second example, currently there is no approved vaccine for the prevention of infection by a certain virus. A clinical trial of possible vaccine is being planned to include subjects treated with the vaccine while other subjects are given a placebo. Okay, so this would be a completely randomized design. Okay, because they're gonna select subjects from a sample and they randomly give some of the subjects the vaccine and they give the other ones a placebo. Okay, and just so you know, a placebo is kind of like a fake drug, because maybe sometimes like kind of like the effect of going to the doctor. Well, at least I get that when I go to the doctor. Sometimes I feel better before the doctor even walks in, right? But partly is the fact that you're doing something about your condition, you already feel better about it, right? So that the fact that you're taking a pill, and some of the placebos are like a salt tablet that has no effect on anything. They take people take the tablet, and it has a psychological effect of that they're doing something about their condition. So that's the placebo effect. But we do that so that we can compare to see, okay, are people actually having just a placebo effect, or is there actually a true significant gain in this injection or pill or treatment that we're applying? Okay, the last one. So that one's the vaccine one, that's completely randomized. So Lipitor, a clinical trial of Lipitor treatment is being planned to determine whether its effects on diastolic pressure are different for men and women. Okay, so the most appropriate here is a randomized block. The blocks would be the women and the men, and you would randomly select from each of those. Okay, so we just have one more. A study of on the next slide would be slide 47. A study of an association between each ear is used for, or which ear is used for cell phone calls, and whether the subject is left-handed or right-handed was conducted. The study began with a survey emailed to 5,000 people belonging to an otology online group, and 717 surveys were returned. Otology relates to the ear and hearing. Is the study an experiment or an observational study? Okay, so the key to being an experiment is having a treatment, right? And an observational study, you're just kind of observing. You're not doing anything. You're just observing. So there was no treatment applied. There was nothing given. It was just question asked to the respondents. So this is no treatment. It's not an experiment, so therefore observational study. Okay. Next question would be, what percentage of the 5,000 surveys were returned? Does that response rate appear to be low? In general, what is the problem with the very low response rate? Okay, so if you calculate the percent, it turns out 717 divided by 500 is 0.1434. which turns out to be 14.34%. So that's a pretty low response rate, and this may indicate you might not get a representative sample because maybe only certain types of people responded to that. But this is a real issue with surveys in general, the response rate, right? So half the time they call me, too busy, I tell them no. Other times, you know, I know what they're trying to accomplish because I'm a statistics teacher. So I ask them how long it'll take, and then I'll do the survey with them. Okay, just because I feel bad. But but that's something you have to take into account for. So if the rate was maybe 20%, that means if you send out 100 surveys, you only get 20 back. Okay, so you have to start planning ahead of time. You know, for purposes of getting back surveys. If you want 100 surveys at a 20% rate, is that you would need 500. You need to put out or make 500 phone calls or put out 500 pieces of email. Then you'll get that 100 surveys that you're looking for estimated. So that's slide 47. Slide 48. I think we'll just kind of hold off on. It's not really. It's just kind of talking about different programs. Just a reminder though, get a TI 83, 84 plus. We will use it in this classroom, and you'll have a hard time without it. So make sure you get it. Okay, thank you.